After a few exact solutions of the 1D Ising model, let me get back to mean field theory again in order to finish up some pending work, which is essentially the Landau's theory of phase transitions. So, to getting at that, we need to get back to the mean field theory, and we will talk about the magnetization, which we have already talked about. We just remind you of the essential results, and here we will talk about the susceptibility and the free energy, and this free energy will be written in terms of the order parameter of the system, which here is the magnetization, and then we will derive a free energy functional in terms of orders, or rather powers of the order parameter, which is magnetization here. And that is where we will end this discussion on the Ising model. And just to remind you that we have done this transfer matrix, which is an exact solution of this Ising model, and also have done the renormalization group, and these are really nice solutions that gives us results that are intuitive, and they are quite correct in terms of qualitative nature of them. Mean field theory, on the other hand, is true, or rather it can be done in any dimension. However, we know that in one dimension we get wrong results. However, in 2 and 3 dimensions, or rather greater than 1 dimension, we get qualitatively nice, or rather correct results, and which are important. So, we get back to the mean field theory, where we have derived that this is also called as a Bragg-Williams approximation. So, we will write down the magnetization, and this magnetization has this form. So, m is equal to tan hyperbolic beta, and well, let me use another bracket here, and it is a h plus z j m, and this h is the external field, z is the coordination number, which means that in fact the dimensionality really enters through this number. Then z equal to 2 in 1 dimension, equal to 4 in 2 dimension, and 6 in 3 dimensions. J is of course the Ising interaction strength, or it can also be called as a Ising parameter, or basically the nearest neighbor spin exchange term, and this m is of course the magnetization. So, you see that this is really a transcendental equation, because what you want to solve is there in the left as well as in the right, and we have done this solution. And what we have also seen, that the critical properties of this magnetization, or rather how exactly it behaves at temperature very close to Tc. To remind you, this beta equal to the inverse temperature, which is 1 over kT. And in order to do that, what we did was that this we took it as H effective, and then we have done a expansion of tan hyperbolic x, and which gives you x, where x is equal to H effective here, which is nothing but it is equal to x minus x cube by 3 plus of the order of x terms, which are of the order of x to the power 5, and higher than that, which we have neglected, and we have kept only terms up to cubic in x, and that gave us this expression for magnetization as beta z j m minus 1/3 beta z j m whole cube. That is x minus x cube by 3. So, this is the magnetization expression for T just below the transition temperature, and this is of course equal to 0 at T greater than Tc. So, for T greater than Tc plus, Then we have actually calculated this m to be equal to or rather this equation, if you gather everything or m on one side, then what you get is that T c over T minus 1 whole 1/3 T c over T whole cube m square, and this is equal to 0. This is for this limit where this m is non-zero, because m is 0, it does not make sense. So, it is T equal to T c minus or T going to T c minus, and this equation has to be solved in order to get m as a function of T for the temperature to be very close to T c, but approaching T c from below. Just to remind you that T c is equal to Z j over K, the Boltzmann constant, where Z is the number of nearest neighbors, which is called as a coordination number, and J is the Ising interaction strength. So, if you solve this, then m becomes equal to plus minus root over 3 T over T c square and T c minus T divided by T c, and this is a form for m that is close to T c approaching it from below. And if you introduce a reduced temperature T, so this is called as a reduced temperature. So, this is equal to T minus T c over T c, and then m becomes equal to plus minus root over minus 3 1 plus T whole square into T. So, here of course, we know that T is weakly negative, because we have temperature which are slightly lower than T c. So, with this, if you use a binomial expansion of this thing inside, so it is a 1 plus T whole square. If you use a 1 plus 2 T and neglect all other terms, so then it becomes simply, so this is of course valid for T to be much smaller than 1. So, m becomes equal to plus minus root over a minus 3 1 plus 2 T into T, which is nothing but equal to minus of 3 T. Okay. So, this T is the reduced temperature, and we are getting a negative sign inside the square root, but there is nothing to worry, because T, the small t itself, is negative, and that is the property, or rather that is what the magnetization is if you approach in terms of temperature, if you approach T c from below. Okay. So, that is the critical property. So, one can write it as m T, and really we are talking about 0 field. So, this is equal to a plus minus a 3 T to the power half for T less than, T tending to T c minus, it is equal to 0 for T tending to T c plus. So, if you are approaching it from above, then it is equal to 0, and this result of course is very wrong in one dimension, because we are talking about the external field to be equal to 0, and still we are getting a magnetization, and which we should not be. There should not be any ordering in one dimension, only in 2 and 3 dimensions there would be ordering. So, but in this simple result that we have obtained is qualitatively correct in 2 and 3 dimensions. That is a remarkable fact. Okay. So, let me now do the other thing, which is called as a susceptibility. Which is a response, rather a linear response of the system as a magnetic field is put in. And let us talk about the isothermal susceptibility, and so we just do it at a given temperature, and this is defined as del m del H at a constant temperature. Okay. And now, if you look at this expression that we have written earlier, this expression that is on the top of the slide, and take a derivative with respect to H, and then we get this chi of t is equal to 1 divided by cos hyperbolic square beta H plus Z j m and a beta 1 plus Z chi of t. So, that is the expression that we get, and again we have to gather this susceptibility chi of t on one side, and then one gets chi of t at t h is equal to some beta divided by cosine hyperbolic square beta h plus Z j m and minus beta Z j. So, this is the form of the susceptibility at constant temperature. So, explore the behavior for H equal to 0, that is the external magnetic field equal to 0. So, chi t, now it is a function of t and 0, this is equal to beta divided by cosine hyperbolic square and a beta Z j m and minus beta Z j. Okay. That is a simple expression that we have. So, this is for the susceptibility. Now, let us do the same analysis as we have done it for the magnetization, that is, we want to see it how it behaves for t close to T c as we approach T c from both below and above. Okay. Magnetization is 0 above T c, does not mean that the susceptibility will also be 0 above T c. We will see that just in a while. So, for now, for t equal to T c plus, or as we were writing it with a tending to sign. So, T c plus, we have m equal to 0. So, chi at T c plus for the 0 field is equal to beta divided by 1 minus beta Z j, and this is again equal to k t minus T c, reminding you that T c is equal to Z j over k, and this is nothing but equal to 1 over k T c and 1 over T. T is the reduced temperature. So, this is the form for the susceptibility, which is above the critical temperature or the ordering temperature, and if you take it for T c minus, that is below T c, basically very close to T c, we know that the behavior of m is that it is equal to plus minus root over of 3 of this 3 mod t, which we have found earlier, and then we can use this expression that cosine hyperbolic x is equal to 1 plus x square by 2 plus order x to the power 4. You know where it comes from, because this cos hyperbolic x is equal to e to the power x plus e to the power minus x by 2, and then for small x you write exponential of x is x 1 plus x square by 2 and so on, and then you can just add all of them and then you get this. So, this is the cosine hyperbolic x. So, around x equal to 0, that is small x, we get the chi of t at T c minus 0 is equal to this beta divided by 1 plus half beta Z j, and then we have a 3 t whole to the power 3 t. So, sorry, 3 into t whole to the power half, and that is your so there is a this bracket here, and there is a square here, and then there is a square here as well, and a minus beta zj. Okay. So, this is the expression for the susceptibility at temperatures close to Tc, but approaching it from below. So, if you make a simplification, pardon me, simplification of this, one gets that beta 1 plus 3 beta zj square into this reduced temperature minus beta zj. And this is nothing but equal to half 1 over kTc, again using Tc equal to Zj by k, this becomes 1 over T. Okay. So, it is interesting that it goes as 1 by mod of T for temperature greater than Tc as well as temperature less than Tc, though with this coefficient to be exactly half of what it was for T greater than Tc in this particular case. So, we sort of take these results and we say that T 0, this is equal to some coefficient, say let us call it some alpha over T for T Tc minus, and this is equal to twice of alpha over T for T equal to Tc plus, where alpha is equal to 1 by 2 kTc. Okay. So, if you plot them, then of course, what we get is that we see that the susceptibility as a function of temperature, it has a behavior. We will have to be a little careful because they have different coefficients, otherwise this the behavior is somewhat same. So, this is for T greater than Tc, the right hand side is for T greater than Tc, and the left hand side is for T less than Tc, and this is how the critical behavior of this this susceptibility looks like. Okay. So, having done the magnetization analysis and the analysis of the magnetic susceptibility, we can now go into the free energy, the expressions for free energy, and see that how it looks like. Just a little bit of algebra, but there is nothing much to worry. It is a simple algebra that we are going to do here. So, F and let us write it, the mean field free energy is equal to, and we will write it for H equal to 0. So, this is equal to minus kT log of Z mf. Okay. And to remind you, the Z of mf which we have derived earlier is exponential minus beta j z n m square and 2 cosine hyperbolic beta h effective whole to the power n. This for n spins, and h effective, just to remind you that it is equal to h plus zjm, and h is the external field. So, this h effective is the effective external field which takes into account that this coordination number and all that. Okay. So, we want to calculate that at 0 field what happens to the free energy, and in order to do that, let me write this expression down. So, this is n z j m square over 2 and minus n k t log of 2 and minus n k t log of cosine hyperbolic beta h effective. Okay. So, that is the expression that we have. Now, what we do is that we will expand this in order to write this free energy as powers of this magnetization that we have obtained. Okay. And in order to do that, let me sort of give you without a proof the log of this cosine hyperbolic x. This can be written as a slightly complicated expression, but not that we need everything about it. So, we have a minus 1 whole to the power n, 2 to the power 2n minus 1, and then there is a zeta function 2n, and then we have n pi to the power 2n and x to the power 2n. The coefficients are called as Bernoulli's coefficient anyway. But if you look at the first few terms, then this is equal to x square by 2 minus x 4 by 12 plus x 6 by 45 and so on. And we really would ignore these terms in order to write the free energy, and so we write this as F mf. So, this is equal to n z j m square over 2 minus n k t log 2 and minus n k t, and what you have is the beta square and z j m whole square divided by 2. That is the first term, and the second term is beta to the power 4 z j m to the power 4 divided by 12, and chopping it off here, not writing the other terms, which are x to the power 6 and x to the power 8. And if you do if you introduce this, maybe just doing a bit of simplification would help. So, this is equal to n z j m square by 2 and minus n k t log of 2, and then you have a n z j m square divided by 2 k t and plus n z, there is a plus sign here, and z j m whole to the power 4 divided by 12 k t to the power cube and so on. Okay. So, and introducing again T c, which is there is a t here which I forgot. So, n k t log 2 plus n k t c divided by 2 t and t minus t c into m square and plus n k t c to the power 4 t cube and m to the power 4. Okay. So, that is the expression for that. So, we have been able to write this FMF in the powers of m square and m4 and so on. And so, we can write this that FMF for h equal to 0, we sort of bring back the fact that h is, we are doing it at h equal to 0, that is the external field equal to 0, it is equal to some F0 plus a t minus t c m square plus a b m to the power 4. Okay. And you can keep higher terms or rather higher order terms with M6 and M8 and so on, but this is good enough for us, and this F0 is just a constant term. It really shifts the energy up or down and it does not have any sort of importance in the equilibrium state of the system, and we can actually ignore this for the moment. So, ignore for now, and then we can draw this, this is again for h equal to 0. So, we will just do this FMF this is just a sketch freehand drawing, and we get a parabola for FMF as a function of m for t greater than Tc, and you see that there is no magnetization here. M equal to 0 is the only solution for this problem. Okay. And at t equal to Tc, we see that this parabola become like a cup. Okay, so pardon me for this, it's just a freehand drawing. So it becomes like a with a broad base, and it's rising absolutely symmetrically. That's what is demanded by the formula. And the important thing is that at t less than Tc, so this is at t equal to Tc, and then sort of, so this is the so you get for t less than Tc, you get a plus m, I mean this is minus m and this is a plus m. So the minimum of the free energy are obtained at two values which are symmetrically placed about m equal to 0. And so basically if you cool the system below Tc, then the m equal to 0 solution becomes kind of metastable, and any perturbation that the system receives will push it down to either plus m or minus m with equal probability. So now this situation changes a little when you put in presence of a magnetic field. So this is H equal to 0, and if you go to H not equal to 0, then the free energy actually picks up a term which is H not equal to 0. So this is equal to FMF, which is F0 minus HM plus A T minus Tc m square plus some B m to the power 4 and so on. So this is the new term in presence of H not equal to 0, and accordingly these plots that we have presented in the last slide, they get skewed in one side. So this becomes like it's like this, it becomes asymmetric. So this is F MF versus M. So this is T greater than Tc, and similarly for T equal to Tc, you will have so the T less than Tc, we have this thing becomes so this is FMF versus M. So this is skewed, but it has two minima. One of them is of course deeper than the other. So the system would like to be in this region, and for this is for small h, that is small magnetic field, external magnetic field, and if you increase the magnetic field, then it becomes pretty much like this. Okay. So then of course there is no other solution but for the magnetization to be in the direction of the field which is caused by this. So this is for large H. Okay. And importantly, we have written down a free energy expression in terms of this. So this free energy expression is written in terms of some constant term. Let me ignore that constant term, at least write it as A, and then there is a term which depends on T, and it goes as T minus Tc, and then there is this this m square, and then there is this C which goes as m to the power 4. So this coefficient that depends upon T, this coefficient does not depend upon T. One can write further terms, but the physics is not qualitatively changed if you write further terms. These are good enough for us to analyze this problem. So, if you go to this these two plots, so at h equal to 0 you do not have t greater than T c, there is no magnetization. At t equal to T c it becomes flat, and at t less than T c there are magnetization at even at h equal to 0. So, this result is wrong in one dimension, and they could be qualitatively correct in 2 and 3 dimensions and so on. And then if you put a magnetic field, this at t greater than T c you still do not have, so this is really flat and so on. So, there is no minima, but so there is no magnetization because the free energy does not show real minima at a non-zero m. This is very shallow. Okay. The one that you have is that if you put so this is for t less than T c, and again this is for t less than T c. Now, t less than T c there is clearly a minima that is shown, which is equal to some one of these m 0 which in the direction of the field, and for large field of course there is a unambiguous minima and so on. So, this m equal to m minus m 0 that stop becoming a solution at large fields. Okay. So, that is pretty much what we do with the Ising model, and its various solutions have been shown. We have shown the transfer matrix, we have shown the renormalization group, and have convinced you that they give right results in 1D, and qualitatively I mean you can't do a renormalization group in 2D, but there are other solutions that are possible. And then we have done a mean field theory earlier, and here this analysis actually serves to give you two perspectives, or rather 2 point of views, and they are what are the critical behavior of the observables. That is, how does the magnetization behave below T c and above T c. Of course, above T c the magnetization is 0 in the absence of a field, and so we want to know that how it behaves for t close to T c, either you approach it from below or you approach it from above. And the same we have done for the susceptibility, and the susceptibility is the response of the system, that is how the magnetization changes as a magnetic field is being or in presence of a small magnetic field. And then we have calculated the free energy, and we were able to expand the free energy by in terms of the order parameter, which is magnetization here. And why is the magnetization is the order parameter? We have drawn this before, that this is really we have this magnetization to have a form like this. We have also drawn it in the other side, but this m as a function of t behaves like this, and this is the T c, and this how it behaves, or rather how it vanishes in the vicinity of T c is what we have shown. But this magnetization is non-zero for t less than T c, and magnetization vanishes at t greater than T c. So, magnetization is a marker of the phase transition, or it indicates phase transition, and that is why it is called as the order parameter. So, the free energy is expanded in terms of the order parameter, and it is important for one to note that there are only I mean the even powers are only present, and because odd powers would make it these terms to acquire a negative sign as m goes to minus m, which in this case is not acceptable. Here m goes to minus m, the free energy does not change, and so this is the order parameter, and we have been able to expand free energy in terms of these order parameters. And so there is a very general theory which is developed by Landau, and it is called as a Landau's theory of phase transitions, and very well applicable in superconductors and in magnets, and in a limited sense we have shown this thing to arise for the case of magnets. So, with this we will end the discussion about an interacting model, a really simple interacting model, but have shown a number of important facts and techniques about this model, which is known as the 1D Ising model. And of course, we have not done much about any exact solution in larger than one dimension, but qualitatively this mean field theory gives you results which are correct and intuitive in larger than one dimension. Of course, in one dimension it fails miserably. Okay. So, we shall stop here with that and continue with other topics, newer topics in the next discussion. Thank you.